what in the world is space-time? And I'm going to start with ether, because the ether has something to do with space-time, okay? Um, General relativity, special relativity. It kind of led to relativity and also quantum mechanics for that matter. And it's because in the 19th century, pretty much everyone believed in the ether, that there was this medium out there, what I call a bunch of particles, okay? A lot of people get offended. They say, oh, it's not a bunch of particles. And yeah, it's a bunch of particles. That's what the ether is. And what the scholars of the 19th century believed was that light was a vibration of the ether, meaning what? Of the particles of the ether, which is the correct way of saying it. When people say it's the vibration of the ether, that's where they make the big boo-boo, grammatical and semantic error, and they don't realize that. They say, oh, it's the vibration of the ether. You can't say that. That's like saying that it's the vibration of the forest. Well, you can say the vibration of a tree. You can say that the tree is shaking, but you can't say the forest is shaking. Okay? And that's the difference between a particle or a few particles within the ether that make up the ether, and to say that the ether is vibrating and that a electromagnetic wave or a transverse wave is the vibration of the ether. No, the forest does not vibrate. There's no waving of the forest, because if the forest waves, then it waves with respect to something outside the forest. Forest is not a physical object. Now, it could under one context. You go to a kindergarten and the baby, the 2, 3, 4-year-old toddler, he goes in there and he draws something. And what does he draw? Well, he draws, a green region on his paper. And someone asks him, what is that? And he says, that's the forest. Okay. But then you can't go in there and say, well, the tree the air is blowing one of the leaves of a tree. You can say, you can't talk about the tree because the forest is all the trees, and now we're going to talk about the forest. You either talk about tree or you talk about forest. You can't say that because a forest is made out of trees and the wind blew the tree and shook the tree, that the forest is shaking. And that's the error these people commit with the ether. They think that because light is the vibration of the ether, when they really mean vibration of the particles that comprise the ether. If you're going to talk about that, talk about the particles. Don't talk about the ether. Okay? Ether is the whole shebang. You can't say the whole shebang vibrates. Okay? I hope someone got the message. Okay, anyways, we start with issue a person raised, and he says, Bill can't explain where the ropes comes from. The origin of the ropes are from the medium itself that they called ether. An etherist guy here. Which is not a bunch of particles, as he states. It's conceptually an incompressible fluid. Okay, let's look up what a fluid is. Fluid is a liquid, gas, or other material, blah, 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 blah. So what's a liquid, gas, or material? Well, you look them up, it's a bunch of particles. So all he said is that, yeah, the ether is a bunch of particles. But Bill said it's a bunch of particles. I don't agree with him. I think it's a bunch of particles. He says it's the fluid. What is a fluid? There is no physical object called fluid. Okay? Like there's no physical object called solids or gases. Okay? These are categories, what they call states of matter. So you can't say that ether is a fluid because you haven't said anything. And again, you either talk about the ocean or you talk about the drops of water that comprise the ocean, or the molecules that comprise the ocean, or the atoms that comprise the ocean. Okay? You can't say the ocean waves because, a little bit of water waved. You either talk about the little bit of water, or you talk about the ocean. You can't talk about both. You can't generalize and say the ocean waved. If the ocean waved, then the ocean waved with respect to something else. Okay? Let's get the semantics right. People never learn to talk. And so these people are confusing, the particles that comprise the ether with the ether. Okay? And regarding what he said, that ropes, he says, I can't explain where the ropes come from. I've already mentioned that quite a bit. So let's go through it one more time. Single thread is all there is in the entire universe under the rope model. This thread turns into ropes, atoms, ropes, atoms, ropes, atoms. We're done. It's been there forever. Why? Because something cannot convert into nothing, and nothing cannot convert into something. We're done. So there is no origin to matter, as in religion, as in mathematical physics, where they say that matter came into being. And people say, well, that's not really what Big Bang says. Big Bang just stops just short of that, just shy of that first frame of the film. Well, they're wrong also there, because it turns out that in quantum mechanics, They say particles coming from the void. They're created from nothing, and then they go back to being nothing. So in mathematical physics, they do have creation of matter. They say nothing turns into two particles, and two particles turns into nothing, called a virtual particle. That cannot be experimentally verified. It's just mathematically put ad hoc. Am I getting through to anyone there? Okay, so that's the issue. The issue is, yes, mathematical physics, like traditional religions, believes in the creation of matter. They think that space, nothing, can turn into something spontaneously. Length, width, and height suddenly pop in. The rabbit pops in from nothing. That's what they believe in. And what we're saying is, no, matter is eternal. Why? Because matter cannot turn into space, nothing, and nothing, space, vacuum, cannot turn into something. 3-dimension, length, width, and height. Period. We're done. And because space is not a thing, it does not have a surface, it does not have form, therefore no object, not even God, can leave space because there is no boundary, no surface to cross, because space is nothing, meaning it has no shape. I hope someone got that. Okay, but where do we get this ether thingy? Okay, well, let's go back in time because people still insist. No, the ether is something that's not a bunch of particles. So let's prove to these people. They like proof, they like evidence. Okay, let's prove to them that the ether is bunch of particles. That's the definition of ether. Again, ether is not a physical object. It's a concept, abstract concept, means bunch of particles. Bunch of particles does not an object make, okay? Bunch of particles is not an object. Object is that which you can point to. You point to an elephant, not to a bunch of particles. You point to the table, not to a bunch of particles that comprise the table. Table is the whole thing, not each individual particle, the billions of particles that comprise the table. Okay, we got that? My God. Okay, so here we have it. We have Robert Boyle. He's one of the first guys who did it, who came up with this notion of ether. Actually, it was several people. Torricelli before him already talked about, particles of the vacuum, or whether the vacuum was comprised of particles. Another one was von Guericke, who did the first vacuum pump. Anyways, ether consists of subtle particles. That's what Robert Boyle said in around the 1660s. In the 1660s, he said this. Or maybe even a little earlier, maybe late 1650s. Anyways, Isaac Newton, I do not know what this ether is, but if it consists of particles, right, particles, then they must be exceedingly smaller than those of air. The exceeding smallness of its particles, talking about the ether, of its particles, right? I hope people are listening. I said the word particle, okay? May contribute to the greatness of the force by which those particles, right, may recede from one another. Thomas Young, a couple centuries later, says the ether consists of mutually repelling subtle particles which are attracted to particles of matter. What is the ether? It's a bunch of particles. Anyone who says anything different is an ignoramus. He hasn't done any research on the word ether. They start using the ether. They say, oh, the ether does this, the ether does that, and they don't even know what the ether is. So when I tell them it's a bunch of particles, they say, oh, what do you mean? What are you talking about, Bill? What do you mean it's a bunch of particles? Yeah, that's what it's always been. Since the days of the Greeks, it's been a bunch of particles. There has never, in the history of human existence, any other proposal than particles. It's always been particles. You talk about waves, it's particles. You talk about magnetism, it's particles. It's done with particles. It's mediated, it's simulated with particles. You talk about field, particles. Energy, particles. Mass, particles. It's always been particles. Where have you been? There's never been any other proposal until I came along and said all atoms in the universe are physically interconnected. There's a single thread in the universe. That's a totally different setup. Until that came along, it's always been particles. Both the official mathematical establishment and the dissidents, they all believe in particles. There's not a single person on planet Earth that has ever come up with anything other than particles. So when you say, oh, it's a fluid, oh, it's a field, what are you saying? What is the field? What is the fluid? Particles. That's what you're saying. You may not like it because you never thought about what you're talking about, but that's what it's been. And that's what all these people used to say. It's particles, 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 particles. You won't get away from particles. And I'll beat it into your brain that it's particles. It's always been particles. Okay, here's the next group of people. More evidence, more proof for those who believe the ether is something other than bunch of particles, right? James Maxwell, ether medium for a propagation of light waves. Light must be a wave process in a medium rather than a substance. Well, what is the difference between a medium and a substance, dear James? Okay. And then he goes on and shows how the phenomenon of polarization fits in with wave theory. Okay, great. Properties of the ether include all these things. Well, what is he talking about? If it's elastic, if it's got density, what are we talking about? Well, he's talking about particles. Okay? And then he says he distinguishes ether from gross matter. Well, how is it different? I mean, we're talking about particles here and particles there. Dirac, another notion that came later, again, it's an ether. And what was it? A theoretical model of the vacuum as an infinite sea of what? Particles. Math physics today, virtual particles. That's what they're talking about. Excitations of the underlying fields. What are fields? Particles. But are temporary in the sense that they appear in calculations of interactions. The accuracy and use of virtual particles in calculation is firmly established, but they cannot be detected in experiments. I love that. They can't detect it in experiments, but it's been firmly established. Why? Because they're particles. Because they simulate everything with particles. So anyone who says that ether's not a bunch of particles, this is the homework you got to do. You got to tell me what it is in it instead. And don't tell me it's a field. Don't tell me it's a fluid. You got to come up with a physical object if you're going to use ether as a physical object. And it can't be the whole thing. If you're going to talk about the ether, we're going to talk about the whole shebang. You can't say, well, some vibrations of the ether here inside is what light is. You can't say that. Okay? Because then you're talking about the particles that comprise the ether. You got that? Okay? Let's hope that sinks in. Okay, and here we have Robert Laughlin, and again, I've mentioned this a couple times before, but here one more time, the modern concept of the vacuum of space, confirmed by every day by experiment, is a relativistic ether, but we do not call it this because it is taboo. This man with a Nobel Prize, hopefully he outranks you, so you better listen to him. He's saying that the vacuum that is used today by both quantum mechanics and general relativity is an ether, but they don't call it that because the word is a no-no. Ever since they got rid of the ether word, they don't want to bring it back, but it's an ether. And why is this important today? Because space-time, as you will see, is an ether theory. Okay, we'll get to that in a second. Okay, here's the dynamic ether. You ever wanted to know what ether looks like? Okay, well, I can't show you what it looks like in one shot because it's always moving around. Remember that ether vibrates, meaning the particles of ether are vibrating. Here they are. That's the ether. You always wanted to know what the ether looks like. There it is. I made it visible for you. All that invisible stuff that's in the background, And you might say, well, light is the waving of the ether. Okay, so here's a waving of the ether, okay? But are we talking about the waving of the whole ether, the whole shebang? Or are we talking about, what are we saying here? We're saying that maybe it's just a few particles that are vibrating. Is that what the ether is? See, you either talk about the whole shebang and say the whole ether waves, or you don't use the word ether. You have to talk about the particles that comprise the ether. And otherwise, you got to tell me what the ether is. And so here's a static image of the ether, okay, for those, because some people believe that the ether is static and light moves through it, okay, and so here it is. That's the static ether. You might say, well, that's the ether, okay, so now you have it. So you got to tell me what the ether is, and you can't say, well, ether is a bunch of particles because that's a definition. That's not a thing, okay. You can't say then the ether vibrates, okay. So either you point to the ether and tell me what the shape of it looks like, or you tell me what each individual particle looks like, and for that matter, you would have to tell me what encapsulates each particle. And here, let me show you an example here, okay? This is a particle, okay? It's white. And we don't care about the particle. We want to know what the black stuff is, which is the one that nobody wants to identify. Everybody wants to talk about the particle and say, that's a particle of ether, or that's, a field particle, or a particle of energy, or a particle of mass, or whatever. We don't care about the particle. We want to know what the black stuff is that contours, gives shape to the particle. And the reason for that is if you have many particles, like in this case here, okay, for you to identify each one of those particles as a separate, discrete entity, it's got to be separated from all the rest. Otherwise, this would be a single block. And so we need to find out what the black stuff is. That's what we're interested in. That's what nobody can identify. And you might say, well, that's space. Okay, you got to tell me now what space is. And the question is whether space is an object, because you say space, but so far you haven't said anything. All you said is that's X. And so I want to know what that X is what is that black stuff? And you say, well, that's space. Is space a physical object? Is it finite? Is it infinite? And some people say space is infinite. Others say space is finite. We have all these versions out there still. After 10,000 years, we haven't resolved that issue. You have people on one side and people on the other side. They just use it any way they want. and you say, okay, so what is a space? Is it an object? Well, if you're going to talk about being finite or infinite, you're applying an adjective in physics. Remember, we're talking about physics, not ordinary speech here, okay? You're applying an adjective. You can only use adjective to describe objects. And so if you say infinite or finite, you're applying an adjective to a noun. You're treating space as a physical object either way. So it doesn't matter. And so assuming you say that space is a physical object, you got to show me the space, the shape of space. And okay, you say that's what the black stuff, that's what space looks like. Now you got to tell me what the white stuff is. What's contouring space? And hopefully you don't say that white stuff is an object too, because then I'm going to ask you what contours that. And we can go on ad infinitum. And that shows you why at some point the buck has to stop. You can't continue pushing the buck. Some point you got to tell me what contours it all. And you can't keep pushing it out into no man's land and say, well, I don't know what's out there. Then you don't have a case. In science, it's very simple, very straightforward. Space is that which doesn't have shape, meaning there's nothing outside of space, because otherwise it would have shape. Okay, and so space is that which doesn't have shape, serves as backdrop, if you could call it that, to matter, which is what has shape. Okay, so the objects like atoms and so on, they're all contoured by this space thingy, which is not a thingy. It's just that which doesn't have shape. And because it's that which doesn't have shape, it's not infinite or finite, because it's not an object. Nothing is a concept, not a thing. Okay, that's why it's called nothing. It's the opposite of thing. Okay? So thing is that which has shape, and nothing is that which doesn't have shape. They are antonyms. Nothing is what gives contour or shape to what does have shape. Okay, provides a contrast. And so something cannot turn into nothing. Nothing cannot turn into something. Therefore, the somethings have always been there. The thread has always been there. The thread had no origin. There's no God that made it. If God made it, fine, he's in here with us. He's trapped in this prison together with us. Like I say, space is the largest prison never built. You can't build, you can't create, you can't design nothing. I mean, I do that every day. I do nothing every day. No, you can model, you can morph, you can convert something into something else, but you can't convert nothing into something. And you can't convert something into nothing like they do in quantum mechanics and general relativity. And so, yeah, we have differences of opinion there, differences of theories. Okay, here we have final point here on this one. And this is how quantum mechanics, again, creates particles. They have this energy, negative and positive energy, I guess female and male. And somehow these morph into virtual particles. This is their theory. They say this is happening every day, that particles pop in from the void, and then these same particles combine because one is negative and the other one is positive, and they turn back into empty space, into vacuum. This is the theory that's out there. So yeah, they have creation of matter from the void, and they have matter turning into void as well. That's mathematical physics for you. Why? Because they're not interested in physical interpretations. This is all magic. This is not even magic. It's surrealistic. It has no bearing whatsoever in science. Okay, so for them to say that two particles turn into space, they turn into nothing, what do you mean? Are they still there as particles? And they say, no, they annihilated. Well, what do you mean by that? Well, what did they turn into? I mean, they annihilated. What happened with the matter? Did 3D turn into no D? So these are the questions that they don't answer. They just said it annihilated, whatever that means. And then they say you should study math to find out what that means. It means that turns into a 0. And then the 0 turns into a 10. That's all math. That's got nothing to do with physics. Those are descriptions. Okay, so let's get into the subject matter today. And again, what I want to focus on is not the math. Okay, there's a little bit of math here, but I'm just going to use it to show you what the mathematicians are thinking or how they came to these ideas, not because we're interested in the math itself. The point here is to talk about physical interpretations, about mechanisms of how the universe works. Okay, that's the bottom line. And the issue here is space-time. You know, does space-time have anything whatsoever to do with how the universe works? We don't care about the math. We don't care about whether Einstein broke his head, doing his variables and numbers. None of that is of any significance in physics. In physics, Einstein has to explain why the Earth doesn't fly out of the solar system. That's what he's got to do in physics. And if he cannot explain why the Earth or the moon, or any planet for that matter, or any moon, any satellite, does not leave the solar system, physically, what prevents it from physically leaving the solar system, he cannot explain that. He has no theory. A description, a mathematical description, which is what these people do, is not a theory, but that's what the mathematicians call a theory. So they say, oh, the relativity theory. We're going to find out this so-called relativity theory is not a theory, it's just a description, because the theory is bunk, it's nonsense, it's poppycock. And so, in other words, the explanation they give you for why or how gravity works, that's nonsense. It's total nonsense. That's what we're going to go over. So again, the math is incidental. Okay, don't pay attention to the math. Here we go. We start with this fellow. His name is Abbott. And Abbott is important in this whole thing because he wrote a book in 1884. And that book has to do with dimensions. Dimensions, as Americans call it, British call it dimension. I always use dimension. Anyways, he called it flatland. And here he talks specifically about dimensions. And what's important about this is that even to this day, this book, that's why I say it's the most important book of general relativity. This book is the one that's used to explain to you why we cannot visualize, why we cannot imagine space-time. Why? Because space-time is four-dimensional. Why can't you imagine it? Well, because we are unfortunately three-dimensional beings. We are stuck in three dimensions. And you say, well, what's that got to do with anything? Well, imagine if you were a flatlander, two-dimensional flatlander, you could not be able to imagine a three-dimensional world because you only can see your flat land, your two dimensions. You're a square, a triangle, or a circle. You can't see cubes and spheres and pyramids. And likewise, we cannot imagine the four-dimensional world because we're stuck in this three-dimensional world. That's the analogy, that's the argument, and it all comes from this book. That's part of it. The other part of why this is important, why it's the most important book in relativity, is that, special relativity, it's called special because it's a special case of general relativity. What's so special about it? It's gravity-less. There's no gravity involved in a special relativity. And that's the world of flatland, because flatland has no gravity. You can't fall in gravity because there is no down. Okay, so all you have is sideways motion, and so in a way, Abbott killed two birds with one stone. On the one hand, he essentially described why, many things about the dimensions, assuming that you live in flatland, you would not be able to understand the three-dimensional world. And the other one is that it's a perfect analogy for special relativity, which is, again, a world of two dimensions. You could say there's no gravity, okay, there's no down, okay? Okay, so this is where we start, and where this takes us is that in the this was 1884, 1887. You had these two fellows, Michelson and Morty. They ran an experiment, actually a series of experiments, in which they proved that there was no ether. Of course, many dissidents to this day say, "Oh, there is an ether. You just misinterpreted the results." Blah 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 blah. Okay. So there's a lot of dissidents believe in the ether. The establishment does not. Okay, so assuming there's, 10% of the people out there are people who are interested in the subject and they are dissidents, well, only 10% of them, if anything, believe in the ether. 90%, those who bow down to the establishment, who toe the party line, they do not believe in the ether. Or so they claim. As you saw, Mr. Laughlin, he said they do believe in the ether, they just don't want to call it that because it's taboo. Okay, so a fellow that came right after that, around those days, late 19th century, was Lorentz. And Lorentz essentially made popular what's called the Lorentz factor. And you see it there. It's that little equation there, gamma equation there. Gamma equal to 1 over square root of 1 minus velocity squared over c squared. C squared being the velocity of light squared. What that little equation does is say that as that little v squared, right? As that little v, velocity, your velocity, it approaches the speed of light, 300,000 kilometers per second. As it approaches that, 1 minus that ratio gives you a very small number. And that very small number, when you have 1 divided by a very small number, it gives you a very big number, meaning gamma is a very big number. And they use that gamma, they multiply it times time, and they say, oh, lots of time. They multiply it times weight, mass, right? And they say lots of mass. And they divide length by gamma, and they said, oh, length contracted to very small. And this is where the ideas of traveling at near the speed of light come, where you have length contraction, mass increase, and time dilation. Now this, again, this already was in the 1890s. In fact, it came before that. In 1887, you had this fellow Voigt who already put that little, the key part, which is that square root 1 minus v over c, right? He already came up with that, 1887. Why is that important? Well, because Einstein, a fellow named Albert Einstein, he was only 8 years old at the time. Einstein was born in 1879. So he was only 8 years old when this fellow Voigt, German, right? He already had this square root 1 minus v over c. And so this length contraction was already debated way before Einstein published anything on special relativity and general relativity. We're talking about 20 years before that. And so what do I mean by that? You know, all these people, they worked on this. Lots of mathematicians were working on the speed of light and what happens if you travel at the speed of light. They came up with all these equations. And Einstein's the guy who took the credit. And to this day, he takes the credit for all of it. Everybody assigns all this credit to Einstein as if he was the only mathematician alive in those days. And they forget about all these. I mean, you talk to anyone on the street and say, do you know who Albert Einstein was? And they say, of course I know. You say, do you know who Lorentz was? Do you know who Heaviside was? They would know who I'm talking about. And so all these people came up with all these things. Einstein took the credit. That's my only point. But that's the first point. The second point is what you see there. When Lorentz came up with all this notion, they started looking at whether the ether existed, and they were trying to incorporate the ether within what they observed. They came up with these equations. They tried to justify the ether one way or another because, you know, these people believe strongly in the ether. They grew up with the ether, just like people today grew up with space-time, with black holes and Big Bang. Go talk to them and say there's no such thing as dark matter or dark energy or black holes or Big Bang. They'll kill you. And these people were no different. They were born with the ether, and you can tell them that the ether did not exist. They said, what do you mean the ether doesn't exist? Of course it does exist. But Michelson and Morley proved that it doesn't exist. Well, let's accommodate that. Let's find out if that's true. And so they try to work around that to try to justify the ether at all costs because they believe strongly, this generation believes strongly in the ether. What they did was they entered the rabbit hole because they started working with time. They started playing around with time or with this gamma factor, okay, this Lorentz factor. And so, yeah, it started getting very weird because they started playing with time and they said, well, if we travel at near the speed of light, what happens to length? What happens to mass? What happens to time itself? And of course, what happened here was they forgot about reality and they were just concentrating on math. Why? Because measurement only has to do with math. In physics, we're not interested in measurement at all. We want to have an explanation of how the universe works. We want to know how gravity works. And these people say, let me measure it. So what if you measure it? I mean, you know, here, my famous trick, we let go of the pencil and it falls to the ground. So you measure something. You measure the weight, the mass, if you want, whatever. You measure the speed. You measure how much time. So what? Can you tell me why the pen falls to the floor, not to the ceiling? You can't tell me by saying mass. You can't tell me by saying, gravity. You can't tell me by saying, speed or time. You will not tell me with any of those notions what causes the pen to fall to the floor instead of to the ceiling. Okay, so this is the problem. We had mathematicians dealing with the problem, and they thought they were trying to figure out how gravity works by doing math. And that's where we stand today. To this day, nobody can tell you why that pencil falls to the ground. Not one person on Earth, except us. You know, here we do have an explanation, a physical interpretation, but we're the only group. And so what did Lorentz come up with? Well, he already had the notion of what is known as time dilation. Okay, this is essentially what he came up with. Okay, that you have a train going by, and you have a passenger on the train and a passenger and someone an observer on the platform. And in the case above, we're talking about the passenger on the train. And if lightning hits the front of the train and the back of the train at the same time, the passenger will see the front of the train hit her first before the one in the back because he's traveling in that direction and light has a shorter time to travel to his eyes. Okay, so that's the notion from the passenger's point of view. How about the observer on the platform? Well, for him, it happens simultaneously because he's equidistant from both points, the front and the back of the train. That's essentially it. What this did was introduce the observer into physics, into mathematics, as we call it, okay? Because now people were concerned about what you perceive Why? Because they were talking about measurement. So, well, you're measuring something and I'm measuring something different. Well, that's because you're moving at the speed of light. And so if you move in this direction, I move in the other direction, we're going to have different measurements. And we have to account for that in our measurements. It all had to do with measurement, measurement, measurement. Nothing to do with physics. It has to do with descriptions, with calculating stuff. We still don't know what causes gravity, but these people are talking about, time dilation, mass increase, length contraction, all this nonsense that they came up with. And just to rub it in, here we have Poincaré and Henri Poincaré, and he essentially enunciated the principle of relativity, also given to Einstein. And Henri was quite angry about that. He said, look, we worked, all these mathematicians, we worked for couple decades, at least 20 years, and this newbie, he comes in there and he takes all the credit for it. He's the creator of special relativity. He's the creator of time dilation, all this stuff, when we've talked for 20 years about this. And so, yeah, he wrote a paper there. Actually, he gave a speech, but he wrote the paper in 1904. Remember the annus mirabilis that Einstein had in 1905, 1 year later, okay? And here we're talking about Poincaré. He came to the United States. He gave this speech in St. Louis, and it's called the Principles of Mathematical Physics. And what I liked is in there, one of the headings is the present crisis of mathematical physics. Sounds like the year 2022. We're still with a crisis in mathematical physics. Nothing has changed in over 100 years. And so, yeah, he enunciated Poincaré enunciated the principle of relativity. That's not Einstein's. And he says the following. He says, concerning the ether, he says, the ether is how its molecules are disposed, etc., etc. And then in that same paper, he says, the atoms of ether. What is the ether? What did the etherists believe in? They believed that it was a bunch of particles, atoms, molecules, particles, points, whatever you want to call them. Okay? So the ether was a bunch of particles, a body, a fluid, a field, whatever you want to call it. I don't care. It doesn't matter. It doesn't change anything because fields, waves, vortices, energy, all these words mean the same thing. They are a standalone. They are standing for lots of particles. That's what they're talking about. It's always been simulated with particles, and it can't be any other way because mathematics can only put a value in an equation, and that value has to be represented with a single point. For example, a field. What is a field? A bunch of points. And when you talk about what's the strength of the field here, they're talking about the strength of the field at that point, at that location. And they designate it with a point, with a dot. That's why it's always been dots and points and particles. Nothing's changed. The only thing that's changed when quantum and relativity also came later on, they turned those so-called particles into abstractions. They got rid of the particle altogether. They said, well, what is a particle? It's a vibration of a field. It's the excitation of a field. You're seeing the hump of a field, and that's a particle. So what is a particle? A field. And what is a field? A particle. No different. They're synonyms. Okay, just values that mathematics has invented to try to give some physicality to their equations. That's all it is. Okay, so here we have another fellow who came around the same time, and his name was Minkowski. And what did he come up with? Well, he came up with a notion of space-time. In fact, there's a debate. Some other people lived in those days that also talked about space-time, among them Poincaré. Okay, but he says in this paper he published 1908, Space and Time, he says, the views of space and time which I wish to lay before you have sprung from the soil of experimental physics. Again, all these people thought that with experiments they were doing science. Okay, no, science is not about doing experiments. Science is about explaining rationally. You have to explain, give me a rational explanation for a phenomenon. That's physics. But these people said, I'm going to do an experiment. So what? Here, I'll do an experiment for you. I'll let go of the pen. There it goes. I let go of the pen. It fell to the ground. How many more times should I do it? That's gravity. And now you got to explain it. To say that you're going to do an experiment, what more experiments do you want to do for gravity? You got to explain it at some point, not do experiments. But these people believed in experiments, and to this day, people believe in experiments. They think science is about doing experiments. So do an experiment. Let go of the pen in your house. Everybody today, go ahead and let go of a pen in your house, and you'll find out it falls to the floor. Unless there's, some magnet out there that's holding it up. It'll fall to the floor. How many more experiments do you want to do? What's the purpose of doing more experiments? Now you got to explain it. Why does it fall to the floor? What comes in contact with a pen is the question. Because if you don't put something in contact with a pen, you are doing black magic. You're saying that spirits are bringing it down. You can't say, well, mass and the energy in the field. No, because those are concepts. We need a physical object. You can say that a tree pulled it down. You can say a rope pulled it down. You can say, I don't know, a wire pulled it down. That you can say. You can say a dog pulled it down. You cannot say a field pulled it down, or energy pulled it down, or or mass or gravity or whatever. Okay, you can talk about particles if you're talking about real particles. Then you can say that particles pushed it down. Okay, that's acceptable, as long as you talk about particles. Okay, you would have other problems, but that's beside the point. The point is you can use particles to push the pen down. You can use that. You cannot say a field brought it down or energy brought it down. Those words are concepts. You can't use those words in science. That's like saying love pulled it down, because love is attractive, I guess. Anyways, he says, henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two, space, time, will preserve an independent reality. And so that's more or less 1908. That's when this notion of space-time started taking shape, okay, in the minds of all these mathematicians. And what were they talking about? They were talking about length, width, and height, and time. And they converted time into a dimension, which is what Abbott had said, more or less. And he talked about dimension, he didn't talk about time. But, these were the days where time became a dimension, because people were trying to measure time. They were saying, well, what happens if you travel at the speed of light? Well, then what happens to time? Well, it's stretched, it dilates, and so that's when they got into trouble, because the semantics was not up to par. And to this day, it's not up to par. So they talk about time dilation. You say, what do you mean time dilation? Are we stretching time? Well, you're not supposed to take it so literally. So what did you mean? Okay, I mean, we're going to talk physics. Let's talk physics. Okay, and then this fellow came around in 1915. He wrote his paper, Albert Einstein, and he said gravity is warped time. And he says it's time that is bent, it's warped, and that's what prevents the moon from leaving the Earth, or the Earth from leaving the solar system, or Jupiter from leaving the solar system. Warp time. And you say, Bill, you're making fun of these people. You're not being serious now. No, I'm being deadly serious. This is the explanation you get for why the Earth doesn't leave the solar system. That there's a depression, and the Earth is rolling around the edges of this depression like a ball around a roulette. That's the physical interpretation. That's the mechanism they illustrate for you, okay? You don't believe me? Here it is again. I didn't create this, okay? Here it is, okay? That's the moon, and it goes around a depression. What is that depression into? What is that blue stuff with all these white lines going through it? Well, that canvas is known as space-time. This is you could say a three-dimensional version of space-time. They say they cannot produce a four-dimensional one. Fine, we'll concede for the sake of argument. But what we're interested here is in the mechanism. They're saying the moon doesn't leave the solar system, or doesn't leave the orbit of the Earth, because it rolls around warped time. That blue canvas with white lines, that's space-time. You're bending time. They tell you that gravity warps time. They say these words. So I'm not inventing anything. I'm not putting words in their mouth. Okay? This is the mechanism that they explain. What do they respond when you say that to them? Well, they say, Bill, you're not supposed to take the analogy so literally. Well, if I don't take it so literally, what have you explained? What is the mechanism? Why doesn't the Earth leave the solar system? Why doesn't the moon leave the solar system? If that was just an analogy, whatever you meant by that. I mean, I need to know what comes up against the skin of the Earth, and you're telling me it's warped time, that portion of space, time. Warp time is coming up against the skin of the planet. That's what you illustrated. And then when I say, you mean you have warp time? And you say, we're not supposed to take it so literally. Then what am I supposed to, I'm asking for an explanation why the Earth doesn't leave the solar system. I have to take it literally, whatever you give me. And so here it is. This is the answer they give you, okay? Okay. Says, understanding gravity space-time is like a rubber sheet. Massive objects distort the sheet. And wait, student says, they distort it because they're pulled down by what? And the teacher said, my God. Space-time is like this set of equations for which any analogy must be what? An approximation. What does an equation have to do with this? And so the people who created this say, oh, that's so boring. No, no, it's not boring. It's irrational. The guy is irrational. He's trying to get away by saying, look, you got to study math to understand what we're saying. If I studied all the math in the world, all I would have is a description. I want an explanation of why the Earth doesn't leave the solar system. And if the guy says it's because it's bending, the Earth is bending the rubber sheet, and that's why the moon doesn't fly away, and the sun is bending the rubber sheet, and that's why the Earth doesn't fly away, then that's analogy is what that's what his explanation is. He can't later on deny it and say, well, you're hanging on every word that I say. Of course I do. It's got to be literal. Physics is literal. Okay, you can't BS your way with equations and numbers and variables. That's where the problem is. These people are giving you a description and selling it to you, like a used car salesman or a guy who sells you some snake oil, and it's trying to pass it as an explanation. And when you focus on the explanation, you say, well, it's just a description, mathematical description. You got to take math to understand what we're saying. You got to look at the equations. Those are descriptions. I want an explanation. So they don't have an explanation for gravity because when you call their bluff, they say you're not supposed to take it so literally. That's the answer you get. Okay, so be aware that's what it is, and that it is a description is certified here by Mr. Stephen Hawking. Okay, and here he says an event is something that happens at a particular point in space in a particular time. It is often helpful to think of the four coordinates of an event as specifying its position in a four-dimensional space called spacetime. It is impossible to imagine a four-dimensional space. That's out of his book, A Brief History of Time, bestseller. Okay, and so he's saying, look, this is all a concept. This is not an explanation. Okay, he just thinks that it's helpful to think of it as a four-dimensional, as a four-coordinate event. What is that? That's a description. He hasn't told me why the Earth doesn't fly out of the solar system or why he doesn't fly out of his wheelchair there. Okay, so this is where we stand. They have descriptions. They're selling it to you as an explanation. There is no explanation for gravity, or like Mr. Toth, Victor Toth said a couple of weeks ago, when we analyzed him, what did he say? He says, we're still investigating. Yeah, they're going to be investigating another 400 years because they have no clue whatsoever what causes gravity. And that's what people want to know. The layman wants to know why that pen falls to the floor, why the baby spoon fell to the floor. They don't want you to give them some equation that describes how fast it fell or what the weight was. People want to know the mechanism. And that's where mathematical physics fails. And space-time is not going to help you. Space-time is a four-coordinate description of gravity. That's all it is. Okay. And just in case, to top it off, we have Mr. Eine, and just want to make sure that we understand that he still believes that space-time it has to do with the ether. Okay, says we may say that according to the general theory of relativity, space is endowed with physical qualities. In this sense, therefore, there exists an ether. According to the general theory of relativity, space without ether is unthinkable. He said that in 1920, 1 year after his theory was so-called certified by Arthur Eddington when he did his picture of an eclipse, and he found that a star behind the sun, he could see it. Why? Because he says the light curved around the sun. That's what this poor guy, Arthur Eddington, concluded, that light was bent, as they say today, or warped. It never occurred to him that what he's talking about, not bent, but deflected. Because if he's going to talk about photons, he's got to use the right language. He can't say light is bent. He's got to say light is deflected because he's talking about particles. What is mathematical physics about? Particles. It's always been about particles. They never left the particles. Okay? So yeah, that's the first problem. The second problem is we have a different explanation for that. We don't need the little photons to curve around the sun to be deflected by the warping of space-time, which is a concept. Again, they use space-time as a physical object. When you put it to them and say, are you saying time is warped? Because that's what they're telling you. And they say, well, you're not supposed to take it literally. Then what have we learned? we're running around in circles. We're warp space, I guess. Depression. Okay, so what are my conclusions for this space-time thingy? Here's a rundown. Space-time resulted from the necessity of discarding the 2,000-year-old ether. Towards the end of the 19th century, the ether was dying. And a few people tried to save it at the beginning of the 20th century, but they had no luck. Eventually, the ether went away. Really, the word went away, but the concept stayed, because even to this day, like Mr. Laughlin says, what they deal with is the ether. They just don't call it that because it is taboo. But space-time is an ether theory. What is ether? A bunch of particles. What is space-time? Well, I think you have it there. Distance have never offered an alternative to particles. That's the first thing you need to know. In math physics, and among all dissidents, right? Space is made of particles. Some say space is infinite. Others say it's finite. And whenever you use two adjectives like those, you're talking about a physical object. Adjectives can only be applied to objects. But one of the main points is that space-time introduced into math physics the false continuum, the fake continuity. Why? Because they talk about the space-time continuum. See, with discrete particles, you don't have any continuums of anything. Everything is discrete. Everything is segmented. And somehow you had to tie it all together if you're going to talk about action at a distance. And that's one of the things that general relativity introduced for the first time in mathematics. They introduced continuity, the space-time continuum. In other words, space-time is this rubber sheet that extends all the way from the sun to the earth, from the earth all the way to the moon. So it's a continuous entity, medium. And so now you can talk about action at a distance because you say whatever the earth does here, it affects the moon over there because the vibrations move through the space, through space-time, through the rubber sheet, right? They treat it as a rubber sheet, space-time. It's warped time. And when you confront them, they say, well, it's just an analogy. You're not supposed to take it literally, okay? But general relativity space-time is made of points known as events. That's why it's an ether theory. Each point, I mean, what is ether? A bunch of particles. What is space-time? A bunch of points. What is a point? An event in space-time. That's what it is. So space-time is an ether theory, an ether proposal. It's made out of points, but somehow it's continuous. You see, so they covered all the bases. They said it's discrete, but it's also continuous. Okay, meaning it's all connected. Okay, so they needed to cover both worlds so that they could explain gravity to you. Okay, they say, why does the Earth affect the moon? Well, because it's a continuous rubber sheet. Rubber sheet of what? Of time. Time is a physical object. You're not supposed to take it literally. Space-time is an irrational mathematical theory, meaning it's not a theory at all, it's a description that states that the Earth doesn't fly out of the solar system because time is warped. That's what space-time is all about. They call it a geometric theory of gravity. It's got nothing to do with geometry because geometry, first and foremost, is about figures. The zero-dimensional point, the one-dimensional line are not figures at all, but those are the foundations of geometry. We covered that in last couple sessions. So mathematical physics, especially general relativity, is founded on this notion of geometry, which is in itself founded on irrational proposals, which is the zero-dimensional point, meaning location, and the one-dimensional line, meaning itinerary. Okay, and so that's what geometry is, and space-time or general relativity is supposed to be a geometric theory of gravity. What is it? Space-time. And what is space-time? Time, which is warped, and that's what they say gravity is. I hope you got all that. It's going to be on the test on Friday.